Welcome back, and this is the last in the series of videos looking at Kp, and it covers one of the most difficult concepts in inorganic or physical chemistry, and that's the relationship between equilibrium constants, entropy and Gibbs free energy, because ultimately all three of those are talking about exactly the same thing, the extent of the reaction. In other words, at equilibria, how much product we actually have made. So before we start looking at the notes, it might be a good idea to look back and remind yourself of the entropy equations from your entropy notes. So we've seen in this topic how we can calculate this equilibrium constant, and that gives us a value that is related to the direction and the extent of the reaction. Now in entropy, we looked at exactly the same idea. In other words, if delta S total is positive, then the reaction is feasible in the forwards direction. And the larger that value, the more the reaction goes forwards. In other words, there's a relationship between the delta S total and the equilibrium constant K. Because as this value becomes more positive, your K value becomes more positive. Delta G is obviously related to our delta S because it's minus T times delta S. So again, delta G has a relationship to this equilibrium constant K. Now in this case, K is known as the thermodynamic equilibrium constant and has no units. It's slightly different from Kc and Kp, but there is a relationship between that equilibrium constant and the value for the Gibbs energy and for the total entropy. So we can combine these two equations to look at the overall effect of ln K. Now this is not an equation you're expected to know. You are expected to know these two, but you're not expected to be able to put them together to make this. I'm just doing this as a little exercise to help us see that there is only one particular variable we need to be concerned with, and that is the variable temperature. Delta H is really not going to change, neither is delta S system. R is the gas constant, and as you'd expect, it's a constant. It is just this temperature value which will change things. So it comes back to something we know already, that the equilibrium constant value is only changed by temperature. So that is the only variable, or the only true variable is temperature. So our equilibrium constant will remain constant no matter what the concentrations or the pressure. The only thing which will affect it is the temperature. So using our delta S total equation, we have delta S total is system minus delta H over T, and that is also equal to R ln K. So we're going to be using this expression. Now we're going to do this for an exothermic reaction. So for exothermic reactions, delta H values are always negative. Now, because the delta H is always negative, this minus delta H over T term will be positive. So therefore, the minus delta H divided by T term is positive. So if the value is negative because it's exothermic, this term, this minus delta H over T, is positive. Now, as the temperature increases, we're dividing that positive number by a larger and larger amount. So overall, this term becomes less positive. So as the temperature increases, because we're dividing by a bigger number, this term becomes less positive. So as temperature increases, minus delta H over T becomes a smaller positive number. Because this term here is a smaller positive number, this will become a smaller number, and the K value will become a smaller number. Therefore, K decreases. Because the K decreases, the equilibrium shifts to the left-hand side. In other words, it favours the reactants. Which is why if you raise the temperature of an exothermic reaction, it shifts backwards. And this is the explanation as to why. So we've looked at an exothermic reaction, and we're now going to do the same thing but looking at an endothermic reaction. So for an endothermic reaction, we know that the delta H value will always be positive. Therefore, minus delta H over T will be negative. And that's true in all cases. So what happens as we raise the temperature? So as the T gets a larger and larger number, this whole term becomes a smaller negative number. So as temperature increases, the minus delta H over T term becomes a smaller negative number. In other words, it gets closer and closer to zero. It's never going to be positive because it'll always be negative, but it has less and less of an effect as the temperature increases. We tend to talk about, in terms of exo and endothermic, becoming more exothermic or more endothermic. So mathematically this is a little bit odd, but we talk about it becoming a smaller negative number. Probably a better way of saying that rather than that is it has less effect because you're minusing a smaller number from the delta S system. So as the temperature increases, minus delta H over T becomes a smaller negative number. It becomes less effective, or it has less an effect on the overall system. So the system, the delta S system, starts to dominate, and therefore K increases. Therefore, the equilibrium shifts to the product side, which is why when you heat an endothermic reaction, it becomes more feasible. You've come across this before. You might not have realized it, but you have. If you think back to calcium carbonate and its thermal decomposition. Now, in a sealed system, that is a reversible reaction. In fact, you've done that one. Lower sixth, you heated group 2 carbonates. And this is why you had to heat them, because this is an endothermic reaction. At room temperature and pressure, the equilibrium is too far over to this side. If you heat it, this will increase the value of K, increase the value of the equilibrium constant, and the equilibrium position will shift to the product side. So that is why you need to heat it in a Bunsen burner flame in order to get the carbon dioxide to be given off. And if you know the numbers, you can actually work out the temperature at which this reaction becomes feasible. So that just looks at this short video looking at what the effect of temperature on the value of Kc and Kp. The key thing to remember is that temperature is the only things which will affect Kc and Kp values. They are constants no matter what the concentration, pressure, or whether or not you have a catalyst present. And we're going to look at why that is in the next video. So until then, take care, stay safe, bye bye.